Hello folks, and welcome to this lesson on optical isomers. By the end of this lesson, you should be able to identify a chiral center in an optical isomer and draw stereochemical formulas for both enantiomers. Optical isomers, or enantiomers, are the last type of isomer that I'm going to talk about. Now, the thing about enantiomers is the fact that the structures are all the same, the connections are all the same, and yet there's still something different about these isomers. This is something that can happen when you have a carbon that has 4 different atoms or groups attached to it. When that happens, that carbon is referred to as being chiral. So because of the fact that this is a 3-dimensional thing, and you have 4 different groups, it happens to be that even though the 4 groups are the same, you can still put them into a different arrangement because of the 3-dimensionalness of it. Now, the optical part of optical isomer is that when you put a bunch of one of the isomers into a container, and then you shine polarized light in it, so all of the light is going in one direction, what will happen to the light as it passes through that sample is that it's going to bend in a specific direction. Now, if you take the other isomer, put it in the container, do the same thing, the light's going to bend, and it'll bend by the same amount, but it'll bend in the opposite direction. This, what it does to polarized light, that's why it's referred to as an optical isomer. Now, there are 2 sort of naming systems in a way for optical isomers, or to distinguish between the isomers. One method is the R and S method, and that's based on the structure itself. You draw the molecule in a specific way, and depending on what happens with what is being connected, that determines R or S. You can also see isomers being referred to as L or D. That L or D has to do with the direction that the light is bending. This can't be determined by looking at the molecule itself. You actually have to figure out, doing the whole polarized light thing, to figure out which direction it actually turns that light. I'm not going to go into any more detail about this because I don't expect you to know it, but I did want you to be aware, if you do see R and S and you see L and D, this is where this is all coming from. When you have chiral carbons, the isomers that you get as a result of having chiral carbons are referred to as enantiomers, or you could get diastereomers. There is a difference between them, and these are the difference. Both of them are still stereoisomers, both of them have the same connections, all the same elements, etc. and so forth. However, enantiomers are mirror images, whereas diastereomers are not mirror images. If your molecule only has 1 chiral carbon, then the 2 resulting stereoisomers are going to automatically end up as being enantiomers. They will be mirror images of each other. However, if you have more than 1 chiral carbon, depending on what's going on at each of those chiral centers, you might end up getting the something where they are actually mirror images of each other, but depending on what happens at each of those chiral carbons, they might not end up being mirror images. So the ones that do end up being mirror images are those enantiomers. The ones that aren't mirror images are going to be diastereomers. As a result of this, your enantiomers are going to be optical isomers. They will do that whole thing with the bendy light-y thing, whereas diastereomers aren't going to be able to do that. So diastereomers are not going to be optical isomers. But we are going to be focusing much more on enantiomers for the purposes of this lesson. So something that I'm going to expect you to be able to do is to be able to identify, when you're given a structure, all of the chiral carbons that might be in that particular compound. And when there is a chiral carbon, I will be expecting you to be able to draw enantiomers. So here we have an example of a molecule. Let's take a look and see if we can figure out which carbons are chiral. Now, first thing that you have to remember, you are looking for carbons that have 4 different things attached to it. And we're not just talking about what is next, right immediately next to it, we're talking about all of the different connections. So for example, if you have a carbon and there is a CH3 and then a CH2CH3, those two are going to be different things from each other, and so depending on what else is connected to it, it could end up being chiral. Now the trickiest thing about finding chiral carbons is going to be remembering to recognize the things that are not being drawn, like hydrogens, especially if you're given something like this. Remember, if that carbon doesn't have 4 completely different things attached to it, it's not going to be chiral. Take a look at where your hydrogens are. If it has 2 or more hydrogens, it's automatically not going to be chiral. So let's take a look. In this molecule, we have 3 carbons. The rest are oxygens and hydrogens. So we're going to take a look at each one of these 3 to figure out whether it's chiral or not. Now for this particular carbon, if you take a look at what's connected to it, it is at the end. So it has the rest of this molecule attached to that carbon, but then the other 3 things it's attached to are 3 hydrogens. So we have 3 hydrogens, it is not going to be chiral. Looking at this particular carbon, if we take a look at what's attached to it, now we do have that CH3, so that is one thing. Then we have our OH, which is another thing, and it is different. And then we have this carboxyl group attached to this carbon as well, which is also another different aspect. Now, something you might think, or if you're not being careful, you might wonder, okay, but that's 3 things. It isn't 4. Don't forget, this also has a hydrogen attached to it. And so with that, you have your methyl group, you have a hydrogen, you have a hydroxyl group, and then you have a carboxyl group, all attached to there. So those are 4 different items, and so this carbon is indeed chiral. Now for this last carbon, you have the rest of the molecule on one side, you have a hydroxyl group on the other side, and you have an oxygen also attached to it. Now the oxygen is different from the hydroxyl group, so these two are different things. However, it does not have 4 different items attached to it. It's double bonded to this oxygen, so this carbon only has 3 items attached to it. Therefore, it is not chiral. Alright, so we have identified that there is 1 chiral carbon in this particular molecule. Now let's draw the enantiomers for this molecule. So the first thing that you're going to do is draw one of the molecules. We are going to start with that carbon, that chiral carbon, smack in the middle. We do need to emphasize the fact that it is a 3-dimensional shape because that plays a huge role in terms of the chirality of this thing. And so what we're going to do is we are going to use the wedges and dashes. So 2 of the bonds you're going to draw as being in the same plane of each other, and then you're going to use a wedge and you're going to use dashes to have one coming out of the page and one going into the page. After that, for the purposes of this course and for the purposes of just drawing the enantiomers themselves, you just need to make sure that you have the right things on your carbon. So make sure that they are actually correct to what the attached bits are in this molecule. So again, in the middle we have that carbon, we have the hydrogen attached to it, we have the hydroxyl group attached to it, here is the methyl group, and then here is the carboxyl group. Now if you wanted to expand this a little bit more, that would have been fine, but I'm making things simple for myself. So from here, if you're going to draw the enantiomer, we need to draw a mirror image. So let's set up a mirror image first. So you're still going to have that carbon, and this time the ones that are on the plane, you see that for the one on the left, the bits that are on the left side of that molecule are the ones that are on the same plane. So that means for our mirror image, we're going to take the bits that are on the right side of the molecule, and those are going to be in the same plane. We're going to have our wedge in sort of the same place, and our dashes are going to go back, so you can see how these are mirror images to each other. From here, once you get this set up, just make sure you're putting everything in the same place that they were in the original. You want to make sure you have that mirror image. So the CH3 is going to end up going here, your H goes here, your OH goes here, and then the COOH goes there. So make sure you don't forget hydrogens, make sure you're using wedges and dashes, make sure they're mirror images of each other. So what? What's so important about enantiomers when they have all the same connections? They're basically the same molecule. Well, it turns out that the enantiomers can have different properties from each other. If you take medicine as an example, you can actually have the two enantiomers, and one of them actually does the work, and one of them doesn't do anything at all, or at least it doesn't perform what you want the drug to perform. An example of that is cetirizine, which is also known as reactin here. And yeah, a lot of the times the meds that you're going to get, whatever dose it is, not all of it is actually going to be the stuff that actually performs. This can be an issue because it's not always easy to separate the enantiomers themselves. And as a result, a lot of the times when you do have enantiomers, you are going to get the mixture, and that mixture is referred to as being racemic. That's the end of this lesson. I'll see you next time.